Do you know how misleading numbers can really be? Today I'm going to be talking about how numbers can be really misleading, and I'm going to do it using a real business example. A few quick notes before I get into it. I'm going to be talking about some graphs and tables. If you want to see those, which you don't have to, you can see those on my Substack, emilymallenbeck.substack.com. You can also enlarge these images if they appear too tiny. You should be able to do that by clicking or tapping on them. And lastly, every time I mention dollars, I'm going to be talking about Canadian dollars. Today I'm going to be using data on business innovation and growth that's supplied by Stats Canada. This dataset covers government support and funding, including consulting, research development, partnerships, and exports. On my visualizations, I called this funding for short, but it is encompassing everything I just mentioned. This data also uses the North American Industry Classification System. This is a system that was originally developed by the governments of Canada, US, and Mexico. It's a list of standard industries, which was updated in 2021. It allows for by-industry comparison across countries. However, there are some limitations in classification because obviously businesses are very complex. You can find links for the data set, the Canadian Business Innovation and Growth information, and the industry classification information on the Substack as well. To understand the point I'm going to make about numbers being misleading, you need to understand a couple of terms. The first term is mean, not like mean like being mean, but the statistical term mean. On my graphs, you'll see the mean as the top of the bars, and in the charts, you'll see it as the left numerical column. Regardless, the mean is actually just the statistical term for average. You've probably learned what an average is at some point, but just in case you've forgotten, what an average is you take a group of numbers, you add them all up, and then you divide by how many numbers there are. If that sounded like something that has almost no meaning, I've got you covered with an example. Let's say you're at a store and you're buying 5 products. They cost $1, $2, $3, $4, and $5 each. If you add those numbers up, you're going to get a total of 15, and you are more than welcome to check that. And there are 5 items, so 15 divided by 5 is 3. The average is 3. What you probably don't know about the mean is that it's actually a statistical model. A model is basically anything that we do that represents a whole bunch of data. This is kind of a big concept in statistics, but I'm going to put it a few different ways to help you understand it. A model is a way of talking about data without having to list every individual data point. It's a way of understanding or summarizing the data. It's a way of doing it that is easy to understand. You can also think of it more practically like Lego or wax figures. They're just representations of a real thing. They're also not perfectly accurate, and that's really key here. I just want to make another point real quick that in this situation, the mean is 3, and there is actually an item that is $3. That is not necessarily always the case. The mean does not necessarily have to represent an actual data point. I'm taking the time to explain this to you because I want to make it clear what the mean actually is, because I'm going to make the argument that it can be really misleading. When we report means, we don't usually do that on their own. We usually include another statistic, and in this case I'm going to be using something called a standard deviation, and I'm going to be using that because it's the easiest to understand. A standard deviation basically just represents how far the mean is from the truth. The smaller the standard deviation is, so the closer it is to 0, the more accurate the mean is. The larger the number, the less accurate the mean is. Standard deviation is also in the units of the topic at hand, so today I'm going to be talking about dollars, so the standard deviation is going to be in dollars. We use the context of the units to determine how large is too large. So standard deviation starts at 0 and it can go up infinitely based on the context it's in. So a $100 standard deviation, if you're selling $1 million homes, might be no big difference, but if you're doing 100 different scoops of ice cream on individual servings, that would be very alarming. The standard deviation is represented on the graphs with those vertical black lines. What you should understand when you're looking at this is that the individual components that went into making up the mean will fall between the top and the bottom of those black lines. At least the majority of them will. I promise these concepts are going to make more sense as we go along because I'm going to be talking about concrete numbers. Now onto the actual misleading data. So the first thing that I did was I looked at the spending per year. The spending increased year over year at some level. It's not a real crazy curve or anything like that, which you can see if you look at the graph. Stats Canada recommends caution against this particular analysis. They believe that there's a possibility that these changes are not due to program changes, but actually due to changes in data accuracy. This is the kind of point that I'm reliant on Stats Canada to make because I didn't collect the data myself. However, when I do collect the data on my own, these are the kinds of concerns that I would already be aware of. When I conduct my own research, I work to mitigate these kinds of concerns. The other thing that's really immediately noticeable here are those huge standard deviations. This is a massive red flag that something is going on. What it's telling me is that the mean is actually a very poor representation of the data. What this is telling me more specifically is that there are massive differences in the amount of funding or support that different industries are getting. This is also a prime example of the situation where, yes, the computer can calculate the mean, but by the same token it shouldn't. A couple of key takeaways here is the importance of standard deviations. I've graphed them here to make them easier to interpret. Just the actual numerical value can also tell you a lot. I also want you to pay attention to graphs that you see just sort of out in the wild, because you very often don't see standard errors, period. And even if you do, you often don't know what they are, and those things are both concerning. The reason it should be concerning that you're not seeing error bars is because you're not having any context for how good the mean is, and if you don't have that context, you don't really know if there's a problem with the data. It's also a huge argument for why you need someone on your side who understands statistics, including which ones should be applied, because if you're unaware of them, you don't know what problems you might have. One quick note here before I move on. This is years that are defined by fiscal periods, so starting April 1st, ending March 31st, not calendar years. So I took another look at this situation, and instead of looking at it by year, I looked at it by industry. If you look at the graph in particular, you'll see really quickly that some industries have substantially more funding than other ones. For example, manufacturing gets way more funding than arts, entertainment, and recreation. You would also notice that this massive error bar problem hasn't gone away. So what this is telling me in this situation is that there are massive funding differences even within industries. So again, what we're seeing is that the mean is not a good representation of the data in this situation. I'm going to get really specific here just to help you understand what's going on. I'm going to start with manufacturing. The mean amount of funding for manufacturing is $558 million. The standard error is $262 million. That means that some projects were funded, and I'm rounding here, at about $820 million, and others were funded at $296 million. Now let's compare that to the leather industry. Their mean amount of funding was $415,887. The standard deviation here was $361,470. That means that some projects were funded at $776,000 and some were funded at $54,000. You can see how the mean and the standard deviation are not even remotely on the same scale for leather and manufacturing. I want to talk about what this means and how it shows that the data is misleading. First, I want to be clear, I've done a really lazy job of this to prove a point that you can't be lazy about this kind of thing. Before I did this kind of analysis, I should have been looking through all of the data to see if there were any issues. Now, Stats Canada said that they did this. I wouldn't trust it, I would look over it myself. I also should have looked for things like outliers, so really, really extreme values, or anything else that's a problem that's just like visually noticeably an issue. There are a bunch of other statistics that I should have checked over before this stage as well, but they're beyond the scope of what's going on here. Those kinds of statistics would be really helpful in this kind of context because they would help to describe what's truly going on. In particular, they would also suggest what to use as an alternative to the mean, of which there are options. But if I don't know what I'm doing, or if I'm trying to deliberately mislead, then I'm not going to take those steps. Or I'm going to take them and use them to help make the data more misleading. More than once I've seen something on the news or read about it in an article and then looked at the actual research and wanted to scream because it was so far off from reality. Looking at numbers statistically is complicated. It has a lot of moving parts, and it always has to respect the context that it's in, which means that not a lot of people are actually qualified to not just do this, but to do it really well. There's an argument I can make for you that's purely statistical, but that's going to be more challenging because statistics gets very technical very quickly. In fact, I haven't talked about anything here that's not like a first day kind of thing. What I can do much more easily is give you a sense of context and why context matter. In a situation like this, I would consider a number of factors that I haven't here. One of the things I would consider would be if there are funding differences provincially and territorially. I would also be interested in how much funding is actually available per industry and how accessible it was to obtain that funding. I would also wonder about funding within industries, if there were different kinds of programs, how specialized those programs were. I would also be interested in how many businesses applied per each industry and how many businesses were successful in their application. I could look up online the deeper level breakdown of these industries, but it wouldn't be particularly helpful for me in this situation because I would have no way to retroactively apply that information. The major point that I'm trying to establish here is that there are a lot of different ways to look at data, and that you have to look at data in as many ways as you can. I'm not talking about seeing data in terms of graphs here, although I make a lot of graphs for myself to help understand the data. I'm talking more about seeing something from many different fresh perspectives. I have personally had data sets, and I've worked with others who've had data sets that on the surface made absolutely no sense. Like sometimes it was just like, this is nonsense, and sometimes it was like, this directly contradicts what we already know. And looking at these data sets statistically in a systematic way and making sure that you're doing everything properly, which again, I have purposely not done here, is one way to get that full view, to get a real understanding of what's going on. The other factor is being trained to understand context. It's about being able to understand what matters and also being able to understand how you get that information. So yeah, data can be extremely misleading. And simple numbers like averages that we think we understand can be the most misleading of all. By the same token, with the right tools in place and the right skills, data can be amazing. It can tell wonderful stories, it can give really specific results, and it can help you understand a wide variety of things in really simple ways. Curious about taking these ideas further? I share more about my work and how I help clients at emilymolenbeek.ca. You can also reach me anytime at research@emilymolenbeek.ca. Thanks for listening.